Well, welcome to our next episode in our pipeline webinar series, Pushing Plastic Pipe. I hope you enjoyed the music. Push It Real Good by Salt and Pepper. I hope you enjoyed that little pump up. We're excited that you're here today. We anticipate a large group, and so look forward to the conversation. Upcoming webinars. As most people know, we hold 2 every year, and so we're interested in any topics you'd like to see us discuss. So reach out to me with any suggestions. We try to promote them twice a year. They're always on our external website, though, if you're ever curious to watch previous ones. Education credit. After today's meeting, I'll send out a certificate of completion along with the recording by end of week, so you can self-report any education credits. As always, the recording of this webinar as well as previous webinars are on the geoengineers.com/pipeline webinars site. As mentioned, we want this to be interactive. We have a bit of a presentation, and then it's going to be followed by a panel discussion. And during that panel discussion, we received some awesome questions during the registration process that we will make sure to cover, but also go ahead and throw them in the Zoom chat, and we'll make sure to get them answered as time allows. Disclaimer, the views, information, and opinions expressed during this webinar by our moderator and panelists are solely those of the individuals and do not necessarily represent those of our respective organizations. So at Geoengineers, we always love to do a safety moment. It's one of our core values. So before we start, let's talk pick season is here. Whether you're at the lake, hiking with family, or on a job site with tall grass, watch out for that hidden hitchhiker. A few prevention tips: cover up with long sleeves and pants, treat your gear with spray, and check your skin at the end of the day. I recently chaperoned my daughter's school camping trip, and an hour into the hike, a tick was crawling through another chaperone's scalp. So they are very active this time of year. So don't just step on it or squeeze it. They still carry infectious fluids. Per our AI friend Claude that we use at Geo, the reliable ways to kill one are dropping it in rubbing alcohol or flushing it. So on that happy note, I hope you feel like you got a good safety moment to start your week off. I want to introduce our moderator for today's discussion, John Robeson. He's moderated a few of our others as well as presented at these webinars. He's a principal engineer at Geoengineers as well as our pipeline discipline lead. He's out of our Springfield, Missouri office and brings over 25 years of experience. He's also licensed in 15 states. His expertise is in trenchless, including horizontal directional drilling and direct pipe, and geotechnical engineering on projects not only across the US, but also international. Fun fact about him, he has 5 kids and 2 grandkids. I always tell him, like, how do you have grandchildren already? You look great for being in consulting this many years, John. So let me toss it over to John here, and he will introduce our panelists.
Yeah, thank you, April. Can you hear me?
We can hear you.
Yep.
Can't see you, but we can hear you.
Yeah, sorry, I'll keep working on that video. I don't know what's going on here, but yeah, well, excited to be with everyone today and presenting this webinar. As Urso is going to describe, this is sort of a follow-up to several papers that we've had recently and some interesting work we're doing with the Azuria team. Ursa is going to be our lead presenter. His picture's there on the screen. He's been with us for about 8 years. He's got a PhD in mechanical engineering from Louisiana Tech and focuses on trenchless engineering. Does a lot of pipe stress stuff. And I didn't realize you've been to over 45 countries with decorative plates. I know what you need to have on your wall behind you.
Yeah.
There is that. That's awesome. Okay. Next slide, please, April. Tom's also with us. He's Vice President of Engineering and Technology, Tom Marty with Underground Solutions. 24 years of fusible PVC experience. A lot of technical expertise there. He's in the NASTT Hall of Fame, and he's restoring an old Datsun 280Z. That's really cool. So we're excited to have Tom with us. Michael Garrett is a construction manager with Underground Solutions. First, I guess, is that Michael, is that your first installation? Was in 2006? Oh, you're on mute. I'm guessing that was your first installation there. So he's been doing this a while. He's from Ireland and plays pickleball. So Michael and Tom are going to sort of join Urso as the panel after Urso presents. Maybe roughly half the webinar today will be a summary of all the research, and we'll kind of lay that out. We do ask for your questions. Put them in the chat because we really like this to be an interactive webinar. So again, thanks everybody for joining us. Urso, I'll turn it over to you.
Yeah, thank you, John. Can you hear me?
Yes.
Perfect. Okay, I'll go ahead and share my screen now. Okay. Can you see it?
Yep, got it.
So I'm going presentation mode here. Okay. Well, thank you very much, John. As John mentioned, today's presentation is a compilation of 3 presentations that we have given at 3 different conferences. And to summarize, give you a quick outline or what's coming ahead and during today's webinar is basically we have 3 separate phases when it came to this project with Underground Solutions. The first phase, when we were first approached, Underground Solutions had already done some preliminary testing on full-size pipe samples. And when they approached us, we proposed conducting a different phases when it came to testing the PVC pipe. So the first phase was just testing the pipe in simple compression to gain an understanding of its buckling behavior. So that was presented first at a No Dig show. Let me show my. Let me see. Let me get the laser so I can point to things. Okay, so yeah, that was the first phase, simple buckling. Then we moved on to the next phase, which was a uh, testing the or having an understanding of the buckling behavior of plastic pipe inside of a casing. So that was a more complex buckling behavior. And then we moved on to the last phase, which was a finite element analysis and actually running a computer model to on a full scale installation via direct pipe there. So okay, so what is fusible PVC? Fusible PVC is basically a resin made of polymerization of vinyl chloride. It can be used in numerous domestic and industrial products. We all have seen PVC in one way or the other. It's not necessarily a pipe material for pipe. It is pretty strong material, chemically resistant, and it has pressure applications. Then moving on to that, there is fusible PVC, which combines PVC plastic with thermal bond fusion, just like other plastic products you would weld or fuse together. And it can be installed using conventional excavation or trenchless methods. So current trenchless applications when it comes to PVC, most applications, if not all, currently are in tension. So PVC pipe has over the last 20 years being installed, whether it is via HDD or sleep lining or other installations. It is pretty well established when it comes to its tensile strength capabilities. And most recently, HDD installation and sleep line projects of up to 7,500 feet in length. Okay, so the reason why we're doing this is we know PVC pipe can be pulled, and now we want to find out, push its limits, and see if we can actually push it to explore its applications, not only in HDD or sleep lining applications, but also in microtunneling, direct steerable pipe thrusting or direct pipe, and also if a plastic pipe, if a direct pipe thruster can be used in pullback assist HDD applications there. So some of PVC's mechanical properties: safe pull stress, 2800 psi. That's again pull and tension. Its yield strength, 7000 psi. Modules of elasticity, 400,000 psi. Poisson's ratio, 0.38. And when it comes to HDD applications, its recommended bend radius is 250 times the diameter of the pipe, and that's in inches. So as I mentioned earlier, Underground Solutions had already conducted some preliminary testing. They've conducted, as you can see here, a PVC full-scale testing of a PVC pipe sample in compression. They've also tested not only the compression of the pipe in its longitudinal direction, but also compressing the pipe using the pipe clamps of a direct pipe thruster there. So that was also tested. And here on the right-hand side, you can see a graph where the plastic pipe or PVC pipe was gradually compressed using the pipe clamps up until the point where the testing was completed or stopped without seeing any damage on the pipe. Another testing that was conducted before we got involved with this project was the actual compression of the pipe using a pipe thruster against this block here. As you can see, the pipe was pushed against this thrust block here. And again, it was tested with the testing was stopped before seeing any damages on the pipe. Due to the time that we have for this presentation, I will not go over in detail on the actual testing results on this testing, but it is also not noteworthy to mention that the testing was, when it was conducted on a dry surface, also on a wet surface, and also right on the butt weld of the joint connection between two separate pipe specimens. So, okay, moving on. After we got involved with this project, we proposed to Underground Solutions to gain establish a pretty good understanding of the PVC pipe behavior in compression, just simple buckling. So we reached out to Louisiana Tech, Trenches Technology Center, and that's where we conducted the simple compression testing on 4-inch and 6-inch diameter pipe samples of different lengths. And part of the reason why we wanted to do that is we wanted to, as I mentioned earlier, establish and have a better understanding of the behavior of the plastic pipe in compression before we moved on into more complex analyses and studies. So this is just a refresher on what you would typically see when it comes to buckling of slender members, in this case the pipe, and depending on your connections, as I showed here on the previous slide, this one here represents a pin connection. So we not only tested the samples with using pin connections, but we also used fixed connections in a fixed environment, pin and fixed pin, just so that we could also look at the different theoretical K values that are plugged into Euler's buckling equation here. So here you can see the results of that phase 1 testing. The orange graph, or the orange points here, represents Euler's theoretical buckling results there, whereas the blue points in here, or actually here a zoom in view of the testing results in this area. You can see here where we have different connections. In this case, the fixed connection, pin fixed connection on the light blue, and then pin connection on yellow. So this allowed us to have a good background, solid understanding of the actual PVC pipe behavior in a experimental way. And you can see, as expected, that and also, by the way, all these testing results were completed or finished when the pipe buckled elastically, and that happened roughly at the pipe yield strength of 7,000 psi, as you can see here, represented by the red line. Okay, so after that, as I mentioned earlier, we moved on to the next phase, or phase two of the project, which was to not only test the pipe in simple buckling, elastic buckling, but actually test the PVC pipe in a longer with using longer members. And in this time we had a smaller diameter, whether it was a 4 or 6 inch pipe that was going to be tested inside a casing, which in this particular case the purpose was to make that casing represent the underground space or tunnel that the PVC pipe will be exposed to in a theoretical or in an actual uh, tunneling or direct pipe construction application. Again, pointing out that we also use different connections. In this case, you can see a pin connection, and here you can see a fixed connection. And this was also conducted at Louisiana Tech, Louisiana Tech's Trenchless Technology Center. So here are some other photographs. Here, this was the very first test that was conducted. The lab there quickly realized that they were dealing with greater forces than anticipated. So this was, as I mentioned, this was the first test. After that, lesson learned, they went on and actually added increased the number of bracing points along the casing so that they were able to keep that pipes in place and not have it bent like you can see here. And
Hey,
again,
Urso, just a quick question along the way here from the chat. Were tests completed under same or similar temperature conditions?
yes, yeah, yeah, and again, thanks for pointing that out, John. Yeah, these were tested at similar conditions, the same location, and all that is documented on Trenches Technology Center's report that we got from them.
Yeah, so all the small diameter stuff was all indoors, humidity and temperature controlled. Some of the pictures that Urso showed earlier of the full scale testing, that was outside, very hot temperature and different ambient outside conditions. So
Correct. Yeah. Yeah. So yeah, the temperature was controlled. The humidity was also controlled, and all the samples during the phase one and phase two were tested at the same facility under the same very similar conditions. So again, just pointing out here real quick, you can see the casing, light blue pipe specimen, and then you can see the actual pipe being tested there in the light or violet color there. So we tested a total of 16 samples there, as I pointed out earlier. You got the fixed pin connections, and here are the results. Here you can see that the testing was completed not at the point where we saw elastic buckling, but here you can actually see where the pipe had permanent deformation or inelastic behavior there. And we could see the pipe bending like this with the pin connections, and we could see the pipe actually breaking here on the fixed connections. So that was very important information that we were able to gather during this phase two, and that not only showed us what behavior we see at the end connections, but that information will be later used to have a better understanding at how the pipe will behave at the on the side where you have the tunneling machine at the very front of on the leading end of the pipe, and also on the back end where you have or trailing end where you have the pipe thruster. So very important information that was gained during the phase two testing. And here are some of all the results that we got from that testing here. You can see the pipe on most specimens there with with the pin-pin connection failing roughly at the 7,000 psi yield strength mark there. Okay, so then we used that information, extrapolated that information, and said, okay, so we tested 4-inch, 6-inch, 8-inch pipe samples in the lab. Let's extrapolate that information and see what does that mean if we were to make these type of testing uh, on larger scale, larger diameter samples. So we looked at these numbers, and based on the information that we gathered from the lab testing done during the phase 1 and phase 2, we came up with these projected failure loads. Now, of course, we wouldn't uh, push the pipe to this limit. So some of the preliminary or initial ideas and it are applying a factor of safety to that projected failure load. And in this particular case, what we're showing is the projected failure load in kips in US tons, and then what would that mean if we apply a factor of safety of 2 in US tons. So moving on here, then we moved on to
Ursa, just
yes, John.
another question from the chat: whether a comparative analysis steel pipe versus plastic pipe can be conducted, as this would provide valuable guidance for interpretation and design considerations.
Yeah, so we're working on that right now. Obviously, comparing plastic pipe, in this case PVC pipe, to steel would be a unfair comparison, just because we're dealing with two different materials there. But yeah, I mean that's certainly it is understandable that steel in this particular case is the benchmark or reference point. So yeah, that is in the plans to have that comparison to steal there and use what we know already with, from actual steel pipe installations, and how that understanding can be applied to plastic pipe, PVC pipe. I hope that addresses the question.
Yeah, I think so. I mean, I think probably most folks online are aware that steel is much stronger than
Correct.
plastic, and so we're
Yeah.
looking into this for other engineering reasons than just a head-to-head comparison. So,
Right. Yeah. Yeah. Of course, it would be, just as steel has its limitations on the length of installations that we can achieve. Also with plastic, that would also be part of the considerations of its limitations when it comes to an actual what would be the maximum length that can be installed, PVC pipe could be installed, and whatnot. So yeah. So then moving on to the what I would call the phase 3 of this ongoing study was an actual FEA, final element analysis run. Again, building up on our preliminary or testing done in the lab, building up on that, calibrating the models, and having a good solid background where we could move on more from the actual experimental into the theory that FEA allows us to explore here. So some of the key items here to mention: when we run the FEA, we run a model with a tunnel radius of 3,600 feet. Tunnel length varied from 750 feet to. We run two scenarios, and I'll show those numbers here shortly. We run a scenario where the pipe length was 750 feet, and the other scenario was a pipe length of 1,500 feet. Then we also varied the annular space from 3 inches in annular space and in diametrical, and then also 6 inches diametrical annular space there. Due to the complexity of contact when running FEA models, we simplified it and so far we have run a frictionless model, and we're also obviously exploring the during next steps to look into applying friction to these models. Some boundary conditions: the tunnel fixed in all directions. That means this tunnel, the outer, what would be the ground in this particular case, that's fixed. The pipe cross-sectional area is fixed in all directions leading on the leading end. So in other words, the pipe on the leading end where the tunneling machine is, the pipe cannot move in longitudinal or around the circumferentially there, just because based on the assumption that the MTBM is holding the pipe in place. And then on the trailing end, the pipe actually can move in all directions, but we're controlling, as you'll see here shortly, we're controlling its displacement longitudinally into the tunnel there. So some of the data that I will show here shortly, or at least the actual force that was required to install casing, comes from a pretty well-known project that in Virginia that involved 9 back-to-back direct pipe installations. Here's a photograph of that. So here's the data from that particular project, and just to point out that data was was provided, and it's being presented or used in per the owner's permission there. So as I said, we had 9 paths or 9 installations. Here are all the crossing lengths, very similar lengths, roughly 1,800 feet. And here you can see the maximal total thrust force that took to install each one of these casings there for this particular project. Most of them were in the neighborhood of 120, 150 US tons, but then we saw up to 340 tons of force, or 680,000 pounds there. Here are some details about the casing that was installed at these projects, which was a shore approach, 42-inch diameter steel pipe wall thickness of 0.72 inches, the cutting wheel diameter 44.75 inches. So there you have a roughly a 3-inch annular space there, or actually here, this is radial space of 1.375 inches.
Just to add a little color to that, Ursa, I mean, this project was or did install plastic pipe eventually, and so, but because of the limitations of technology and installation technology for plastic pipe, steel pipe had to be used to create the space for the plastic pipe. Then the plastic pipe was towed in and pulled into the steel pipe. Then the steel pipe was retracted. So I think probably most on the call could understand how, all these extra steps, if we can condense that process. I mean, that's kind of one of the main points of what we're working on here, is to condense that process and potentially try to eliminate the steel pipe. So
Yeah,
go ahead.
yeah, correct. Yeah, thanks, John. Thanks for pointing that out. I mean, that's really important part of why we are doing this, right? We want to minimize the number of steps there, and if we could possibly go and install the plastic pipe in one shot, then that's what we're trying to do here. Yeah, thanks for pointing that out, John.
Sure.
So moving on the FEA, we looked at, as I mentioned earlier, we looked at that 340 US ton force that was required for this installation. We didn't go for the full length of the. We actually run 2 scenarios. As I mentioned earlier, we run a 750-foot long sample and also a 1,500-foot sample. And what you're seeing here is basically, just to give you a quick background on the FEA. When we were looking at doing this, we had to decide on whether we wanted to apply gradually apply the 340 US ton force to the pipe and run the model like that, or what would this force represent in terms of displacement? And if you're familiar with FEA, it is for the computer, it is easier to solve a model that is displacement based versus a model that is force based. And that is pretty much because when you are controlling the displacement, the model in a sense know what's coming ahead. It knows that the displacement will remain gradually increased, versus when it comes to the force, even though you can gradually increase your force, the model cannot predict what will the behavior be on the next round of an increased step on force. So that becomes sometimes highly unstable, especially with models like this where we're running a buckling of the pipe inside the tunnel. So for that reason, we decided to run this using a displacement approach. And so for us to uh, in a sense convert or have a representation of force in terms of displacement, we had to go back to our mechanics of materials book and look at this little formula that you may recall, where we have the displacement, in this case, longitudinal displacement of your pipe is equal to the force times its length over the modulus of elasticity times the cross-sectional area. So using this formula, we estimated that for us to apply a 300 US ton force to a 750 foot member, it would mean applying a displacement of 69.2 inches to the pipe sample in the FEA model. So we told the model, we're having this pipe. We want you to apply a displacement. Remember what I said earlier. We have this side of the pipe, the leading end, that is theoretically connected to the MTBM. It is fixed, but this side here, we're having control of the displacement in the longitudinal direction. So we told the model, we want you to compress this pipe sample up to 69 inches, which in return will be representative of 340 US tons. And so we run that based on this. This is the sample that we run our model with. Is 36-inch nominal size pipe diameter there with a DR ratio of 25. And again, just a refresher of the table that we showed you earlier. We're limiting that number to no more than the factor of safety of 2 here. So we're slightly going over that factor of safety of 2 just because this number here is based on an actual testing or an actual installation that was observed in the field.
Urso, on that subject, we have a couple of questions in the chat about the
Yep.
installation loads, the variability in the installation loads. And so what we saw, and my recollection was I'll just take this one. Uh, the ground conditions were very similar. Of course, you would expect that shore approaches, 9 of them sort of splayed out into the ocean from a single pit. So the ground conditions were very similar. The links, as you saw, were very similar. The limitations on that particular steel pipe were the limits of the machine. So there wasn't a great deal of concern at any of these loads that you see on the screen or even going higher. And so my take on it is that it had a lot to do with how the machines were operated. And when the contractor was trying for a little more production or whatever. But again, these loads were so far below the tolerances or the allowable loads that it was, there was no concern about 340 versus 215 or whatever. They're all below as I recall, 750 tons was sort of our limit there on both on the machine and on the pipe. So hope that's helpful. There was no smoking gun geotechnical condition that caused that at least that I'm aware of.
Thanks, John.
Yep.
Okay, so as I mentioned earlier, these are some of the FEA getting into the results. Here are some of the inputs: 750 and 1500. This should be a feet, not meters. Sorry about that. And then 70 inches and 140 inches in displacement. And this 70 again comes from here. We just rounded up this number to 70. And if you double the length, in this case 1500 feet, you're doubling the displacement. So that's where that 140 comes from. We had a difference in the annular space of 3 and 6 inches. A radius that we used was 3600, and the entry angle was six degrees. So here's a simulate result, the video of. I might have to get rid of the pointer, I believe. Yeah, there you go. So here, before I run this animation, let me just point out that this one is for the 750-foot sample with 3 inches in radial space there. And what you're seeing here is the maximum stress, 4,000 psi there, which is roughly, factor of safety of 1.8. Considering that the yield strength of PVC is 7,000 psi. And again, we're running just a quick summary or refresher. This is a 750-foot segment to which we're applying 340 US tons of force. And what you're seeing here is only the pipe. I hit the tunnel so that it's kind of out of the way of the simulation or the model here. So you can see that gradually being pushed, and obviously this is exaggerated so that we can point out to the deformation. Again, this is the animation here, and you can see something that I would, for the lack of a better word, I would call a local buckling here, and also here, similar to what we saw in during the phase 2 testing at Louisiana Tech, where we saw that deformation, inelastic deformation at both ends.
But those are considerably exaggerated, correct?
Yeah, exactly. Yep. Yeah, these are exaggerated, and again, pointing out to the stresses, these are actually per the model did not reach the yield strength of pipe. And here again, just pointing out to just a zoom in of the areas in question, and again pointing out here that the actual maximum observed stress was at the boundary condition. And just in summary, we need to, as I mentioned, need to run additional models using friction. Also looked at, we saw not inelastic stresses observed on the FEA. Von-Mises stresses up to 61% of SMICE. Here are the results of all the 4 different models that we run. 70 inches of displacement, or 339 US tons, 336 tons, 340. These numbers here in brackets are actually the actual results from the FEA. So we applied this displacement. The results from the FEA yielded 339 US tons of force. So the mechanics of materials equation that we used was fairly accurate with that. Again, 140 inches of displacement, 340 feet US tons of force, the radial space, and the length of the samples, and then here's the maximum stress observed while running these models. So there are several items and things and variables that we could change to further gain a better understanding of the models here.
And just to emphasize again that, not to get too hung up on the displacement, because as Urso said, we selected the displacement method to get the model to close, but
Correct.
we're really trying to get to that 340 tons. So,
Correct.
multiple iterations, obviously, of trying different displacement. If you started with 340 tons or so, I recall you doing that, and the model just would continue to
Yeah.
run endlessly. And
Yeah.
yeah,
Correct. Yeah, it wouldn't converge because the question would be asked, why, do you try running it with force? Yeah, we did, but it would be it wouldn't converge. So
yeah,
yes, thanks for pointing out that, John. This 70, 70, and 140, 140, these are just means to the end of getting these forces to be applied to the pipe.
yeah.
Yep. And
So we've got a couple more questions in the chat. Maybe actually we can kind of pivot to the panel piece now, or so if you don't mind to unshare.
sure. Yep.
Um,
Sure.
One of the questions was, do we have the duration for each crossing? I guess going back to the Virginia installations, we do, Grady. I don't have that information in front of me, and perhaps we'll give another presentation at some point on that as a case study. But I will say once they got the pit built, those things went in pretty fast. So the pit construction and dewatering and everything was the major time there. Another question. In your theoretical calculation, Urso, maximum stress was observed at the ends? Question mark. Is that, or was it more where we had those little kind of buckling behaviors
Yeah. No, it was at the ends.
at the
Yeah,
ends? Okay.
on that third image on the bottom right corner, that's what we were pointing out to. That the maximum stress was at the end.
Okay. All right. Well, welcome, Tom and Michael. We have a couple of questions actually on some folks as they RSVP'd that should be right up your alley. So maybe I'll open up to one of you guys to ask, how are the welds inspected?
The welds are inspected a couple different ways. First and foremost is the training of the operator. We run an extensive 3-day training course for fusible PVC that provides the machine operators with the proper techniques and follow through with the second phase, which is each of our joints is data logged. So we record time, pressures, ambient conditions, heat plate temperatures, things of that nature as well. And thirdly, what we do is we take that information from a project site and bring it back to uh, a central location where not only is the information archived, but we do a review of each fusion joint within 24 hours of it being made. So if there's any anomalies in the fusion process, we're able to catch those and correct right then and there in the field.
Okay. Thanks, Tom. Anything to add to that, Michael?
Um, we record joints in real time, and like if we're doing like a slip line project, we'll get them reviewed in PA before they go inside in the hose pipe. So we can, a whole bunch of joints wouldn't go into a casing without them being reviewed.
Right. Right.
Yeah.
Right. Another question kind of up your guys' alley, I think. Interested in applications for FPVC, including compressed fit installations and where that has been used.
Not sure what a compressed fit installation, if we're talking about a roll down of some type. We have not done that. Typically, when we do a slip line, for example, we're looking for nominally, 1 to 2 inches of annular space to be able to slide in based on the condition of the pipe.
So if I guess to put it another way, FPVC is fusible and you're not doing those sorts of compression connections. Is that fair, Tom?
That's correct, yes.
Yeah. Uh, uh, let's see. From the chat, stresses increased as radial over deflections, but overall jacking forces usually decrease as overcut increases because frictional resistance decreases. A lot of increases and decreases there. Can you see the chat to make sure you understand the question, Urso? Oh, you're muted.
Yeah, John, could you read it again? I don't think I
Okay, yeah,
followed.
sure. So the question is, you concluded that stresses increased as radial overcut increased, presumably because of out-of-plane deflection, but overall jacking force usually decreases as overcut increases because frictional resistance decreases, right?
Yeah, correct. That's accurate, and I think that's why it is important to run these models considering friction as well. There.
Yeah, I mean, I think it goes back to like how you are constraining the lateral movement of the pipe, and by a bigger overcut, you're just allowing it to move. The load is the load is not taking into account the overcut. We're applying a deflection to
Right.
get load, regardless
Right.
of the overcut.
Right. Yep.
Another question, Urso, on the model. Were models run with decreasing elastic moduli to evaluate longer term applied loads or just short term conditions?
Uh, and Tom, correct me if I'm wrong, but when it comes to PVC pipe does not is not affected by load sustained loading as other products.
It's not, you're correct. Other thermoplastics have a time-dependent factor that typically is applied. That's not the case with PVC and FPVC.
Right.
Okay. Another question from the preliminary sign up sheet. Can you address thrust restraint at the end connections to line pipe? Beyond the standard concrete thrust block, we don't like burying our flange connections in concrete for future O&M. So I think the question is other options for thrust restraint other than concrete thrust block. Michael or Tom?
Mike, do you want to do that?
Yeah, we typically see MJ fittings with with megalugs typically. 11 and a quarters coming out of drills, or typical change of directions. But restrained fittings is what we see with megalugs typically.
Okay. Let's see here. I guess there's a question of panelists to discuss when each product is most appropriate to use. I think maybe the answer is that we're still figuring that out. Maybe, I mean, right now, for at least for like a direct pipe, steel is the option. One of the points of all this work is to see at what perhaps shorter distances and lower thrust loads we could use a plastic pipe as the insulation pipe. I don't know if anyone else has anything to add to that.
I think one of the options, John, is the uh, non-corrosivity of PVC, that in some environments and applications, a product that does not have that potential to corrode certainly has steered projects towards a plastic pipe versus a metallic pipe, for example.
No, that's true. And maybe I didn't explain it or convey it earlier. But of course, with electric, you can't leave with the electric project, you can't leave that steel casing in the ground. So that you have to end up with a plastic casing for that application. Another question from the chat. Sorry if this was discussed earlier, but were different pipe thicknesses tested and how that affected the results? Maybe that's for you, Urso.
Different pipes, meaning dimensions. We in the lab we tested different dimensions. So the when it came to the phase one testing, the results obviously were different because we varied the parameters, but the results were consistent with the Euler's theoretical buckling. And then also when it came to the phase two, the results varied because we used different end connections. But that being said, we saw consistency where we had a repetitive testing. For instance, if we tested when you want to normalize the results, if we tested a pin, whether it was a 6 and 8 inch, if you were to normalize the results, there were consistency. We saw consistency there. I don't know if that answers the question.
No, I think that does. Yeah, another question: how do you recommend sealing the annular space between casings from traveling groundwater?
Well,
Maybe
there's a
Mike or
variety of
Tom?
methods. Mike, do you want to go through what we typically see, the type of seals and grouts that we've used?
Um, we've seen, cellular grout usually is pumped in between in the annular space between the casing pipe and our PVC carrier pipe, and vice versa. They've used link seals on casings where we um, go in, which is the typical sealer, and then on jack and bores, like we've used the rubber boot system with stainless steel strapping that seals, and also we've seen like bulkheads, that go in a couple of feet and seals the pipe that way too.
Yeah. Okay. Thanks, Mike. Maybe just in the few minutes we have left here, Tom, maybe you could tell us a little bit more on the history of FPVC, how long it's been in the market, um, where is it extruded, kind of some of those things.
Yeah, we've always been looked at as a new product. We've been around since 2004. Our first job was put in the ground in January of 2004. It was a 500-foot shot of 8-inch pipe in Florida, and have grown from there. It probably took us about 6 months to get our first mile of pipe in the ground after that, but now we're doing that and more on a daily basis. Uh, the longest we've gone, as you'd mentioned in the presentation, is 7,658 feet with a NHDD again in Florida under the Caloosahatchee River between Fort Myers and Cape Coral. And that really was the impetus for looking at compression. At those lengths, you want to have contingency plans, and we really started this thrust testing to see if we could add a thruster to the back to increase our capacity for an HDD installation and provide a higher level of safety factor as a client may need. I believe that job was done in 2 years ago, and I think Bennett Trenchless was one of the designers on that, if I'm not mistaken. We're made here in the U.S. and primarily our pipe comes out of Fargo, North Dakota overall, and we hope to be able to provide pipe in the not too distant future in the next year or so from a plant we're building in Mississippi to exclusively run FPVC and 50-foot lengths for the project and utility users around the country.
All right. Yeah. Thank you. Well, I think we're running up on time here. Want to thank everyone for joining us, and we're always geoengineers always interested in what folks want to hear about. So please get a hold of us and let us know if you have any suggestions for future webinars. We really appreciate your attendance. April, did you have some? I see you came off. You're on screen again. Do you have anything for us at the end here?
Yep, just that I'll be sending out an email. Really appreciate Tom, Mike, Urso, and John presenting today. We hope to have another webinar this fall. Obviously, would love to hear any topics that you're interested in. If you have any follow-up questions today on today's presentation, don't hesitate to email me and I'll loop in our colleagues on the phone right now. So watch for an email from me by end of week with the certificate of completion as well as the recording of this webinar. And we really appreciate you taking an hour of your day out to be with us. Thanks so much.
Thank you.
All right.
Thank you,
Thanks,
everyone.
everybody. Take
Thank
care.
you.